So the next speaker is Francesco Buscemi from Nagoya University. And well, today he's going to be telling us about von Neumann's other entropy, observational entropy, coarse-grained states, and irretrodictability. So please, Francesco, when you're ready.
Okay, so thank you very much. Thank you very much for the kind invitation. And it's always a pleasure to be able to share some ideas with colleagues and friends. So today I'm going to tell you about a recent work with collaborators. Well, first of all, let me tell you something about this painting. This is an interesting thing. So 2 weeks ago, I was at the Yukawa Institute in Kyoto, and I was looking for some proof of connection between Yukawa, the Nobel Prize for particle physics, and Satoshi Watanabe, which was also a physicist around the same time. I mean, Yukawa probably was born 1910 and Satoshi Watanabe 1912, sorry. So I was trying to find proofs that the two have met before and knew each other before. I was pretty sure about that. But looking there in the Yukawa Institute, there are some memorabilia that belong to Yukawa. And I found this one. So this was a gift that Satoshi Watanabe gave to Yukawa in the 60s. And I was trying to find a meaning because, you know, like two important theoretical physicists cannot give each other like just boring plain presents. For sure, there was a meaning about this thing. So I tried to search what this is about. So this is an excerpt from an ancient Chinese poem, and this is called the episode of the happy fish. So here it's written in Japanese, but the poem is a more than 2,000 years old poem, I think, from ancient China, and so it's a long poem, and there is this episode where two people are walking along a river, and one of the two is telling the other guy, look how happy the fish look like. And the other guy asks him, how do you know that the fish are happy? And so they start discussing about, you know, how you can tell what things are. And essentially the moral of this episode is about the role of objectivity and subjectivity when we talk about the world around us. So you can say basically the same thing happened when we say that a system is in a thermal state. How do you know it's in a thermal state? You think it's in a thermal state, right? But you are not that state, right? So like all these things are kind of connected because today my talk will be looking at the foundations of statistical mechanics and thermodynamics and quantum thermodynamics as well. So there could be like a subtitle if you want to this talk. It's a kind of story between three entities. No, there are entropies and there are paradoxes that we want to solve, and then these paradoxes are essentially solved by explicitly introducing an observer into the picture. So we have to see how it is possible to mathematically introduce the notion of an observer in the picture. Okay, so these are the people I had the good luck to discuss with, to develop these ideas. Clive and Valerio in Singapore, Dominic in Korea, and Joe in Barcelona. And recently, Dominic has also founded a club, the Observational Entropy Appreciation Club. You know, you can sign in for free. You don't have to pay anything to be part of this club that enjoys among its members also Wigner and von Neumann. He put also these two guys in the list of members. So if you want to be part of the club, just look for this website. Okay. So first, the entropy. So we all know von Neumann's entropy. It's the entropy. There is even, the factoid according to which it's been von Neumann to suggest to Shannon to use the name entropy for the quantity that characterizes, for example, the optimal compression rate of a source, right? This is apparently not true. So asking Shannon later on, Shannon denies that such a discussion ever happened. But I mean, the name of von Neumann is intrinsically related with our modern understanding of the concept of entropy. So essentially, together with Boltzmann, Gibbs, Shannon, there is von Neumann that essentially pushed the concept further quite a lot. And in fact, if you take a look at von Neumann's book, the book about the mathematical foundations of quantum theory, the book that was published in 1932 in German and then translated in 1955 in English, which is still extremely deep. It's a still extremely deep book. I advise you to take a look at that if you haven't got the chance yet. He devotes a relatively long section to introduce a concept of entropy for quantum systems. And he devises a very, kind of complicated machinery involving semi-permeable membranes and observations and thermodynamic cycles in order to show that if we want to be consistent with the second law of thermodynamics, we should assign this quantity as the entropy of a state rho. So to be more precise, if you have a density matrix rho that it is diagonalized in this way, so here eigenvalues are taken with multiplicity, and so the von Neumann entropy of this density matrix is defined as this thing here. So is the Gibbs entropy, is the Shannon entropy of the eigenvalues of the density matrix rho. So quite ironically, so von Neumann spends a long time explaining why this quantity is the quantum analog of Gibbs entropy. But then just after he finishes his discussion of this quantity, he writes this. Well, this is taken from a previous paper by von Neumann, but essentially the same argumentation can be found also in the book. So he writes, the expressions for entropy given by the author is von Neumann, of course, are not applicable here. And here it was a thermodynamic setting. So are not applicable in a thermodynamic setting in the way they were intended, as they were computed from the perspective of an observer who can carry out all measurements that are possible in principle. That is, regardless of whether they are macroscopic or not. So essentially, von Neumann entropy is something that measures the amount of uncertainty from the viewpoint of an almighty observer. And well, we can make this statement a bit more precise mathematically. So what does it mean? This is a way to put it. Essentially, von Neumann entropy can be seen as an optimization overall measurements. So you can say that if you have an orthonormal basis, or you could also take minimization overall rank 1 POVMs. Like you can try to find the measurement that minimizes your uncertainty about the state, and that measurement will exist, and that uncertainty that you get from that measurement coincides with a von Neumann entropy of rho. So in this sense, von Neumann entropy describes an almighty observer, which is typically not what happens in real life. An observer typically is very limited. And now, in order to continue the discussion, von Neumann poses a paradox. So this is taken from the book. So he writes as follows. Although our entropy expressions, as we saw, is completely analogous to the classical entropy, it is still surprising that it is invariant in the normal, in the sense of Hamiltonian, evolution in time of the system, and only increases with measurements. And the classical theory, where the measurements in general played no role, it increased as a rule even with the ordinary mechanical evolution in time of the system. It is therefore necessary to clear up this apparently paradoxical situation. So what is the situation exactly that von Neumann has in mind at this point? So what he has in mind is the simple and yet a little bit disturbing phenomenon of the free expansion of an ideal gas. So here the idea is that you have two volumes of the same size separated by a valve, and initially you have a certain amount of like an ideal gas that is entirely confined into this left part of the container. So it starts with some initial pressure, some initial volume, and some initial temperature. And then you open the valve and you let the gas expand. Okay, this is completely isolated thermally from the environment. So this container is adiabatic. There is no exchange of heat. The other half of the container is vacuumed. And so the gas expands against the vacuum. So it does no work whatsoever. There is no exchange of heat because the walls are assumed to be perfectly adiabatic. And therefore, what you end up with is with a gas with half the pressure, double the volume, and the same temperature, because there was no change in the internal energy of the gas. Okay, so the gas expands of just Hamiltonian evolution, right? There is nothing here that works against the Hamiltonian evolution. And nonetheless, according to the laws of classical thermodynamics, you have a net increase in the entropy of the universe. Okay, so you have a phenomenon that happens spontaneously and, you know, completely according completely to Hamiltonian mechanics, and yet this leads to a net increase of entropy. So to me, this is not so far, after all, from the black hole information paradox. Right? If you think carefully about it, there could even be some connections between the two. Why? Because this is, of course, so the question to ask is, what is this entropy that increases, right? Because it cannot be the von Neumann entropy, because on the other hand, we know that von Neumann entropy, depending only on the eigenvalues of a density matrix, is invariant under unitary evolution of the system. So this entropy that increases during a free expansion of an ideal gas cannot be the von Neumann entropy. So how can we cure this problem? And an idea comes already from von Neumann that, of course, was very much influenced by the ideas of his senior friend, Szilard. And von Neumann, in fact, continues in his book writing, for a classical observer who knows all coordinates and momenta, the entropy is constant. So if we were able to follow all the trajectories of the particle composing the ideal gas, we wouldn't see any difference. We would just see them, you know, expanding on a larger volume, but still we would be able to trace them back at will. So the time variations of the entropy are then based on the fact that the observer does not know everything. In other words, that he cannot find out, measure, everything which is measurable in principle. So we have to put by hand an observer in the picture, an observer which has some limited capabilities in performing observations on the system. This is the reason why entropy increases. The increase of entropy doesn't tell us anything about the actual physical system or nature, the universe. It just tells us about us looking at the physical system. So, you know, von Neumann doesn't like empty programs. He wants to put formulas. He wants to put mathematics in what he says. So he comes up with this proposal of a new entropy. So this is von Neumann's other entropy, that he argues is the right thing to use for thermodynamic situations, but somehow was just forgotten and overshadowed completely by her more famous sister, the von Neumann's entropy. But von Neumann actually argued in favor of another quantity. So what is this quantity? So he calls it the macroscopic entropy, and it's defined as follows. So you have a density matrix, you have an orthogonal resolution of identity. At the time, people didn't know about POVMs. They were working only with orthogonal projectors. So you have then probabilities here. So a probability that rho clicks on this projector pi I. And then you have these terms that can be considered as kind of volume terms, analogous. You will see from the formula in a second. So using these ingredients, you can cook up this quantity. So this macroscopic entropy of rho with respect to this orthogonal resolution of identity P is given by minus sum of pi log pi plus the sum of pi log this volume, this omega I. So you see already that it somehow interpolates between Gibbs entropy and Boltzmann entropy, right? If you understand these volume terms, so these are the dimensions of these subspaces into which the Hilbert space is divided, but you can understand this in a sense as the volume of the cells in phase space that goes into Boltzmann formula for the entropy. So this is von Neumann's proposal. So what we are going to consider today is a modern generalization of this quantity that employs POVMs rather than orthogonal resolution of the identity. And this quantity is called observational entropy, but it's very similar to von Neumann's macroscopic entropy. So here you see that the only thing that changes is that you have a POVM instead of projectors, but probabilities are still one, and the volume terms now are just the trace of these POVM elements. And it is defined in this way. So exactly, in analogy with von Neumann macroscopic entropy. So this was introduced recently in the literature by Dominic and collaborators starting from 2019. And then they applied it to various situations of thermodynamic systems out of equilibrium. Recently, there was a review paper, a topical review published on PRX Quantum by Strasbeck and Winter, in which essentially they revealed thermodynamics for microscopic systems, so like a kind of quantum thermodynamics, all around the concept of observational entropy. Anyway, that is a different story. I'm not going to talk so much about applications of observational entropy in physics, but I'm going to speak about the mathematical properties of observational entropy and the interpretation of observational entropy, what observational entropy is. So first of all, observational means of the observer. Why? This is very clear. This is something that is made extremely clear by von Neumann already almost 100 years ago. So of course he didn't know POVMs, but he had the concept of observable and jointly measurable observables already. So von Neumann defines a macro observer as a collection of simultaneously measurable quantities. So he takes these quantities to be observables, but according to our modern formula, the modern formulation that we use nowadays, we can say that these quantities are POVMs. So these POVMs form a family of compatible POVMs that can be measured simultaneously. And this is how von Neumann defines a macro observer. A macro observer is essentially a collection of properties that can be measured simultaneously. So we know that there exists one mother POVM and stochastic processings that are able to reconstruct each of these POVM elements only from the elements of the mother POVM. Okay, so essentially we can say that a macro observer is a POVM. There is nothing but that. And then, so this is the POVM that the observer measures, looks at, and then from these outcomes, these classical outcomes, all the other quantities can be derived by post-processing. So what are the mathematical properties of this quantity? So a thing that we noticed, and somehow surprisingly was not noticed before, is that there is a very close connection between observational entropy and relative entropy. So relative entropy is defined in this way as usual. So you have two density matrices, and the relative entropy between rho and sigma is defined in this way. So it works without caveat when the essentially when sigma being 0 implies that also rho is 0. So essentially you can remove that part, the problematic part of the space, and you can focus on the situation where essentially sigma is invertible. Okay, so you focus on the subspace where sigma is invertible essentially, and it satisfies some useful properties. So here, if you have two density matrices, so two operators with the same trace, this is greater or equal than 0. Sometimes this is called Klein inequality in the case in which these A and B do not have the same trace. And then from this relative entropy, you can obtain back von Neumann entropy just by considering here the sigma state to be the uniform state. And then, you know, the crucial property of Umegaki relative entropy, the reason why it appears basically everywhere, it is because it is monotonic under the action of a completely positive trace-preserving linear map, a channel, a quantum channel. So the action of a quantum channel decreases the relative entropy between two states. This divergence can be considered to be kind of statistical distance. Okay, in technical terms, it's divergence can only decrease. The two states can only get less distinguishable if they are acted upon by a noisy quantum channel. So using monotonicity of relative entropy, we are already able to prove a simple bound for observational entropy. That is to say that for any state rho and any P of M P, so remember the P of M is basically the observer, the observational entropy is not smaller than von Neumann entropy. So again, von Neumann entropy in a sense has the feeling of being the minimum uncertainty, like quantifying the minimum uncertainty for an observer. And the proof is very simple. It is essentially a simple observation that the difference between observational entropy and von Neumann entropy is a difference between the relative entropy of rho and the uniform distribution and the relative entropy of the same states acted upon by this CPTP linear map, which is what? This is the map that takes a state into the diagonal of the outcomes occurrence probabilities. So essentially you have in jargon a quantum classical channel that takes a general density matrix into the diagonal matrix where each diagonal entry corresponds to the probability of obtaining a certain outcome. So because this is CPTP map, we can use monotonicity of quantum relative entropy. Therefore, this difference is non-negative. Okay, so we have this theorem proved in basically one line, just by noticing this the connection between observational entropy and relative entropy. So now a very important role in studying the monotonicity of relative entropy is played by Pett's theorem. So Pett's theorem asks the following question, answers the following question. For which triples, rho, sigma, and channel E, does the equality hold? So Pett's in the 80s provides a sufficient and necessary condition for this to hold. And the answer is that this equality holds if and only if the transpose channel, which is constructed in this way. So this is a transpose channel that the transpose channel depends on the channel E and on this reference state sigma. Okay, so it's constructed with making this sandwich with the inverse of the square root here, and then you take the trace dual of E. This is like the Heisenberg picture form of the channel E, and then again you sandwich with the square root of sigma. So if and only if this transpose channel brings rho back. So if you put here in the input E of rho, so the output corresponding to rho, this transpose channel is able to bring you back exactly to rho. And of course, the other equality is satisfied, but this is boring because this is satisfied by construction. So the point is this thing here. It's able to bring you back to the initial state. So a very important thing to stress is that this thing is not the linear inverse of E. This exists also when the channel is not at all invertible, taken as a linear map. Rather, it is related with the idea of statistical retrodiction. And I will come back on this point later. Anyway, armed with Petz's theorem, we can prove the following result for observational entropy. So the minimum is achieved. So the observational entropy is equal to the phenomenon entropy, if and only if rho can be written in this way. So you see that here, I mean, rho can be defined in this kind of recursive way. You can put rho, measure rho, and then take the probabilities that you get from rho, and with this probability construct the convex combination of these things that are density matrices, right? Because this is a POVM element divided by its trace, and you get rho back. So a state that satisfies this condition we call fully observable or macroscopic. And the proof again is a direct application of a Petz's transpose map. So essentially, if you want to see what states satisfy this condition, you have to look at the subspace of fixed point of this composed channel P with the Petz's transpose map of P with respect to the uniform distribution. So you search for the eigenspace corresponding to eigenvalue 1 for this linear map, and this tells you what kind of state satisfies. So at least one will always exist, right? And in particular, what can be this one? If you want an example, like the uniform, of course, satisfies this condition just because you used the transpose channel computed with respect to the uniform. So the uniform satisfies this thing, okay? If not anything else, at least the uniform distribution satisfies it. But typically, you might have more states that are fully observable or macroscopic. Okay, so how does the observational entropy resolves the paradox? So we see basically that observational entropy can increase also under unitary evolution of the system. And also we will understand what it means for it not to increase. We will also get some intuitions in that situation. So let's start from t equal to 0 from a fully observable state. Okay, so at the beginning, we are in a situation of full knowledge. You can say that we prepare the state, and so we know everything that we can possibly know about the state, limited with our observers' limitations given by P. So then the system undergoes some unitary evolution. So it brought from T0 to T1 by means of this unitary operator view. Then you can just, work around things. So what is the observational entropy at time T1? Very well. So the POVM is P. So I work out the observational entropy with respect to POVM P and the evolved state. But I can use cyclicity of trace to bring the unitaries on the POVM elements. And I can put here inside this trace some invisible identity, which breaks down into U daga U. So essentially, the observational entropy at time T1 is equal to the observational entropy at time T0 made with respect to this backward propagated or pullback of the POVM. So what can we understand from this? It seems, we are going in circle, but there are some positive things that we can understand, new things. So in general, okay, in general, the observational entropy will increase. Why? Because in general, these pullback P of M will not be optimal anymore for rho at time t0. P was optimal, but in general, this will not be optimal. And so there is going to be, in general, a greater or equal than relation here. But also we learned that the following are equivalent. Applying Petz's theorem, we can understand what it means that this does not increases. Okay, so typically it will increase, but what does it mean if it does not increase? So these are all equivalent. So on one side, we have that the observational entropy does not increase. This is equivalent to saying that this pullback P of M is also optimal for rho at time t0. Equivalently, by using Petz's theorem, it means that rho t0 can be expanded on these elements of the pullback P of M. But now we've evolved this guy into rho t1, and so you see that this U disappears. So it means that P is optimal also for rho at time t1. So in words, the observational entropy of a fully observable state evolving unitarily cannot decrease, first. And second, it remains constant if and only if the state remains fully observable at all times. So this is telling us something about the situation where here we have the equal sign. So what can we say instead when we have finite differences? So the first thing that we can say is that we have a triangle equality for observational entropy. So the theorem goes as follows. So given a d-dimensional system, a density matrix rho diagonalized with this thing, a unitary operator U that models some kind of time evolution, and a P of MP that models the observer, let us define two joint probability distributions as follows. The first one is PF. F is for forward, and we will understand why. So you take this basis, phi x, you evolve it according to U, you measure the P of M PI, and then you multiply by a prior of choosing this pure state phi x. Versus another joint probability that we call PR from reverse or retrodicted. And it is constructed as follows. So now here you use as prior the PI, which are the probabilities of occurrence of the outcomes. According to this PI, you prepare density matrices PI divided by VI. These are density matrices because it's a positive semi-definite operator divided by its trace. And you evolve these things backward in time with U-DAGA. And then you measure the P of M that corresponds to the basis that diagonalize rho. Then the difference between the observational entropy at time t1 and the phenomenon entropy at time t0 is exactly equal to the Kalbach-Leibler divergence between the forward probability distribution and the reverse probability distribution. What it means? It means that we are comparing, statistically comparing two situations, the situations where you have, you can visualize it as, time flowing from left to right. So here you pick some pure state phi x with this probability, you evolve them with U, and then you measure the P of M PI. This builds up the forward joint probability versus this thing, which is to sample these states that are just obtained from the P of M. So you turn the P of M into an ensemble, and the probability that you use to sample these states is now the probability of the outcomes. And you backpropagate it through U-DAGA, and finally you measure phi x. This is the reverse probability. So here we are going towards some notion of, rather than forward and backward in time, rather I would say prediction and retrodiction. And indeed, this picture perfectly fits within Richard Jeffries' theory of probability kinematics and the definition of statistical retrodiction in classical inference. So how do we understand this as a notion of prediction and retrodiction? Okay, so start from the forward probability distribution. So this was constructed in this way. So you remember you have phi x, the projector on phi x, and you evolve it with u. Okay, so it means that the cat evolves with u, the bra takes a u daga, and then you have the POVM element here in the middle. Okay, so if you want, you can write it as lambda x, the prior, times some conditional probability distribution pi f, f for forward, that given an x gives you the probability of observing some I. Then notice that the marginals of these things are, on one side, if you discard the I, you get the eigenvalues of rho. And if you discard the x, you get exactly the probability of occurrence of each outcome pi. So you can write it if you like as this. So this is a kind of weird notation, doesn't make so much sense, but it gives you an idea. So you start from a probability distribution on the lambdas, this lambda x, and then you propagate this through this channel, this stochastic processing pi, obtaining the prediction that corresponds to the prior. So you have a prior, you evolve the prior through this channel, classical channel, and you have a prediction. This prediction, of course, corresponds to the Born rule. These are the probability of each outcomes as Born rule tells you to predict. So you can see this forward in this way. So you start from a lambda, you have some kind of prediction rule that gives you what is going to be the outcome distribution. So now let's focus on what happens for the reverse distribution. So this is defined in this way. So in the middle now you have the POVM divided by VI, and then you daga again, and then you have this phi x, that were the measurement that you do afterwards. And remember, it goes backwards. So if you want now, you can write it in this way. You have, as a prior, you have this pi, and then you have some pi r of x given I. So now you start from the probability of the outcome, and you predict a distribution on the eigenvectors of the state. So you do backwards, you go backwards. So now let's take a look at this, and let's write this in a slightly different way. This pi r. Okay, so the channel, the classical channel that gives you how to do inference from the outcomes back onto the input. So this is this, right? So you write it in this way, and here I'm writing just VI again in a different way. You see, I'm just taking PI, I'm turning it with some unitary, which is pointers, because anyway, then I take the trace as sum over x. And then I put this dummy constant, d to the minus 1. But d to the minus 1, what it is? This is the uniform distribution. So I can write it as ux. And here, what I have, this is the forward probability. This is the pi f of I given x. So this guy here, what it is? This is exactly, I don't know if I wrote, yes, this is exactly the Bayesian inverse pi tilde u of this process. So a process where I start from a uniform prior on the eigenvectors, and I evolve this uniform prior with this channel pi, the same channel pi. So this is a process, and I construct the Bayesian inverse of this process with respect to the uniform distribution, and I use this inverse to backpropagate the PIs. So it seems strange, like there are two priors. So I do the inverse with respect to the uniform, but then I use this Bayesian inverse to backpropagate the PI. But this is perfectly fitting within, as I said before, Jeffrey's probability kinematic. Why? Because PF now corresponds to the prediction that we do starting from some prior that we have on the lambdas. So this is the inference about the measurement outcomes. And what Jeffrey tells you to do, if you want to instead to do retrodiction. So PR corresponds to the retrodiction where you start from this new information P on the outcomes, and you backpropagate according to this Bayesian inverse done with respect to the uniform. So in other words, this is the inference about X, about the input, that a completely uninformed Bayesian agent would do if given information about I in the form of the probability distribution P. So you have to imagine that you're sitting at the end of this circuit. You're only you know the POVM, you have information about the distributions of the outcomes, and now you want to retrodict something about the state that was at the beginning of that was input in the POVM. So what do you do at the beginning? You start with absolutely no information about the prior, and so it is reasonable to say that you start from a uniform prior on the lambdas. And you use this in order to backpropagate your new knowledge. This pi for you is new information that you can use for retrodicting, about the input. So this is exactly what happens. So essentially what it tells you that the equality here between these two things, between observational entropy and phenomenal entropy, occurs if and only if predictor and retrodictor agree. You can imagine that there are two agents. There is an agent that is sitting on, at the beginning of the circuit where the states are prepared, and this predicting agent is predicting the probabilities of outcomes. And on the other side, you have a retrodicting agent, the retrodictor, that is sitting at the end of the circuit and can only look at has information about the outcome probability distribution and uses this in order to retrodict something about the input state. And this brings me back to Watanabe, because this is exactly the point of Watanabe's contention about understanding of time reversal symmetry in physical theories. So his idea is that the phenomenological one-wayness of temporal developments in physics is due to irretrodictability and not due to irreversibility. So essentially, the second law is not telling us anything about a physical arrow of time, but is only telling us something about an inferential arrow. And this is a concept that we explored together with Valerio and Clive in a couple of papers, which we focused instead more on statistical mechanics and fluctuation relations, where also a notion of reverse process plays an important role. So essentially, you can somehow forget about ideas like to time inverse, or when people say, I do, the time. I think I even said that before a few slides ago when I was doing UDAGA. So I evolved it backwards in time. We cannot turn time backwards. We cannot do that, right? And so the only thing that we can do is to retrodict. But still, everything would follow. Like, we need not any notion of time reversal here in order to understand the second law. We can work only with retrodiction. Okay. And then we can say even something more. So until here, the story reads pretty nicely. Everything, everything falls into the right place. So it's very satisfying from the conceptual viewpoint. There is only one aspect that, one can argue whether this is really the thing. Like, this is, okay, there is a quantum system evolving in time, but it is otherwise entirely classical here. So what I'm doing is basically classical prediction and classical retrodiction. I'm working with classical probability distributions. Can we say something about the quantum process? Can we say something about non-commuting entities? Well, we don't have an equality, but we have a bound which is pretty strict, pretty tight, by the way. So the bound is the following. So before we had that this difference was equal to the classical relative entropy between the forward joint distribution and the backward joint distribution. But we can say that this is also an upper bound between the quantum relative entropy between rho and this rho tilde r, which is what? This is the state retrodicted by the later observer. So we can imagine that this recipe can be thought as a sort of quantum retrodiction, which is a concept that is not yet completely developed in quantum theory. But it seems again to be fitting into the picture. So like to consider like Pet's recovery map as a form of quantum retrodiction. And still we would saying that essentially if this change in observational entropy is small, then these two states that need not commute, by the way, right? Because here you see that rho r is taken to be a kind of convex combination of these things, and in generally these things do not commute with rho. So this is a genuinely quantum divergence here on the right, but still we can say that if this difference is small, then these two non-commuting states are close to each other. And this is even like it's a strengthening of some results in the theory of approximate recoverability, where typically people have either a measured so-called measured relative entropy, which is optimized over measurements, or the logarithm of the squared fidelity, which are both less tight than this bound. So this bound somehow in this particular scenario, it improves on previous results taken from the theory of approximate recoverability. So let me jump to the conclusions. So take-home messages. So when the use of fundamental entropy in thermodynamics is problematic, for example, in describing the entropy change in a free expansion, so try consider observational entropy, because von Neumann told you so. So we have to obey the authority. Okay, so because this is why I like observational entropy very much. First of all, because observational entropy has a fully operational / inferential definition. So we like operational theories, and observational entropy seems to be tailored for that. You do not need to you need not know rho. That's the point. You only need to know your measuring apparatus and the probability of the outcomes. Then observational entropy describes thermodynamic scenarios avoiding interpretational paradoxes. And this is always good. If you can avoid a paradox, it's good. Paradoxes are bad. We want to get rid of paradoxes. We don't want to make new paradoxes. Even though there is, there is a school that wants always to put forth new paradoxes, but we don't want paradoxes. We want to solve paradoxes. And then observational entropy fits nicely within recent developments in quantum mathematical statistics, so we can bring about all the super powerful tools that people have developed in the theory of approximate Pet's recovery. And also, like, it is tantalizing to see whether there could be some connections with black hole information paradox, where, by the way, the Pet's recovery map is coming up again, not by chance, because it's retrodiction, and retrodiction is all there is to cosmology, right? And observational entropy suggests a natural candidate for quantum retrodiction, as I said before. So you can say, well, okay, let's imagine that Pet's map is actually the right way to do quantum retrodiction, and indeed, you can bound things. I mean, it naturally comes into the formula. It seems, the mathematics is suggesting you the way to understand these concepts. And this is all, and I thank you for your attention.
Thank you, Francesco, for the nice talk. Are there any questions? Okay, I see someone is raising his hand. Please go ahead.
Okay. Hi, Francesco. So first of all, I would definitely subscribe to this observational entropy club, because I like this concept very much. Okay, as you said, so this operational entropy is a Kullback-Leibler divergence.
Yes.
If you want, between this, okay, if you go back to the very first definition of it, in which it seems to be that, okay, you assume, say, as a prior, the uniform.
Yes.
The identity.
Yes.
And what if I have a different prior?
Yes.
What would happen?
You would just be able to do retrodiction in more general situations. So this is actually something that we are working on at present. You see, so here I was able to do this trick. I was able to do this trick exactly because the unitary preserves the identity matrix.
Yes.
Okay, so if I put here a channel that is not unital, then it seems like I'm stuck. Right. And indeed, there are there is some literature that say, you know, there are some no-go theorems about the fact that you cannot have this kind of discussions about time reversal and so on if your channel is not unitary nor unital. But the point is that you are just missing a prior. So if you want, adding a prior would not only, you know, be a kind of mathematical curiosity to make the thing more general, but it would also allow you to consider here general channels, general CPTP maps. So the thing should be changed, but then, you know, you have to argue whether, again, if this fits within Jeffrey's narrative of probability kinematics. And yeah, like we have results in that direction, just we are still working on those. But it's spot on. What you said is perfectly, it's pointing in the right direction.
And another question, if I may, and what about the properties of this entropy here when this would be kind of fairly straightforward, but when you have tensor product Hilbert spaces, so
yes, depends on, so it depends on P, right? So it starts, everything starts with defining an observer, and this observer is a classical observer. This is a kind of macroscopic entropy. So then, yeah, you have to tell me what the observer can do on a tensor product, whether the observer can measure also entangled POVMs, or whether the observer is limited to only measuring locally and maybe separable measurements. And also, for example, this entropy would not be the thing that you want to use in order to discuss things like entanglement, right? So entanglement would be something that happens in this kind of unobservable sort of quantum degrees of freedom, because here, once you measure everything, I mean, the entanglement gets destroyed. So this is really something, you know, this is a beautiful quantity, but it has its own limit of applicability, of course, like everything, right? So this is really something that is related to a macroscopic observer looking upon a quantum system.
Okay. Thanks, Francesco.
Thank you.
Are there any more questions?
If I may ask a very quick, perhaps naive question.
Yeah, of course.
So, Francesco, thank you very much for this very interesting talk. Unfortunately, I had to miss the first 15 minutes, so that's my question is probably naive, but at some point you define states. I don't remember the name you give them, but states for which the von Neumann entropy and the
like
observational
macroscopic states, perhaps.
No, I think it was before this, for which the von Neumann entropy and this. Okay, exactly. Yes. I was wondering if this this right-hand side of this two-way implication, if you think there could be also like a closed form characterization for any POVM of all the rows for which this is the case, if this is trivial or maybe not
question.
interesting.
I thought a bit about that, and it's kind of easy to find it if these things are orthogonal, right? Because it means basically that your main density matrix is diagonal on those blocks. But if these are POVMs, then some weird things can happen, right? So what you should look at is essentially the eigenspace corresponding to eigenvalue 1 of this CPTP map.
Yeah.
this P composed with this P tilde U. Yeah. So then, yes, there are some, for example, in the lecture notes by Michael Wolf that you can find online, there is a long section about fixed points of quantum channels. So, for example, in the case in which this inverse is done with respect to the prior, to the uniform prior, then you know that this is going to be an operator system because identity is contained in the set. And so you have very powerful algebraic tools to characterize the set, and probably this gives you a way to have an explicit characterization. But in general, I don't know. Perhaps there is. It would be very nice to see an explicit characterization of these states.
Thank you.
Thank you.
Okay, are there any more questions?
Yeah, there is something in the chat, right? Could you please elaborate a little bit more why observational entropy would not be a good tool to measure entanglement unlike phenomenon entropy? Because well, I have to be honest, I didn't think much about that, but because it's all the definition begins with someone doing a measurement on the system. Then I suspect that phenomena like, for example, negative coherent information, or actually, well, negative conditional entropy, that is to say positive coherent information, that is a signature of quantum entanglement, all these things would not be there with observational entropy. But it's a feeling that I have. I actually didn't think carefully about the problem.
All right. Yeah, Francesca. I mean, I have a few questions, but I think we can discuss them later on, right?
Okay, very good. Yes, it's better to move on. Yes, I'm already late, 7 minutes late.
Okay, perfect. Yeah, no, thank you very much, Francesco. Yeah, very thought-provoking talk. Right.